Welcome to KU Parasala. I am Dr. Hubert, Associate Professor, Department of Physics, University of Kerala. Today I am going to deliver the talk on the best is yet to be Raman effect, past, present and future. Sir C.V. Raman is an erudite scientist, gifted speaker, reputed teacher and professions writer. C.V. Raman, childhood and early life, he was born on 7th November as second child of Chandrasekhara Ramanathan Iyer, who was a teacher and Parvati Ammal at Tiruchirappalli, Tamil Nadu. In 1904, finished his graduation from Presidency College, Madras with Army Gold Medal for Physics. In 1906, at a very young age, he observed the diffraction of light through an oblique rectangular apparatus and developed mathematical equation to explain his observations, which was published in British Journal, Philosophical Magazine, and also published a paper on optics in Nature. In 1907, he has completed MA course from Madras University with record marks, married Loga Sundari Ammal, posted as the Assistant Accountant General to the Finance Department of India, Calcutta, found opportunities for carrying on experimental research in the laboratory of the Indian Association for the Cultivation of Science at Calcutta. In 1912, awarded the Horson Research Prize. In 1913, received the Woodburn Research Prize. In 1917, joined Calcutta University as Polit Professor and Head of the Department of Physics. In 1926, started Indian Journal of Physics. In 1928, discovery of Raman effect. In 1930, Heitz Medal by the Royal Society London, got Nobel Prize in Physics. In 1933, appointed as the fourth director and the first Indian director of the Indian Institute of Sciences in Bangalore, that is known as IISc. In 1934, founded the Indian Academy of Sciences, IAS. In 1935, received the decoration of Rajya Sabha Bhushana by Maharaja of Mysore, and he bestowed the land of 10 acres for the establishment of the Indian Academy of Sciences and the Raman Research Institute at Bangalore. He was the director the years 1948 to 1970 of Raman Research Institute. In 1954, awarded the highest civilian award, Bharat Ratna. 21st November 1970, he was died. This photo shows that Raman early used his experiment for his discovery of this Raman effect. With the spectrometer is shown here with the source, sun source is the source and eye is the detector, is the instrument Raman used for the discovery of the Raman effect. His contributions: Raman inherited scientific temper to study astronomy, physics, mathematics and acoustics from his childhood. From 1907 to 1922, Raman worked extensively on acoustics. He made valuable research on mechanical theory of strings, instruments, especially of violin family and frequency of mridanga. He studied whispering effects under domes of the Victoria Memorial, Calcutta, the Gold Gumbaj at Bijapur, the Granary at Patna and St. Paul's Cathedral in London. He made his own scientific interpretation for the secret of blue color of the sea water, which contradicted the earlier theory of the blue color of sea by Lord Rayleigh. Raman postulated that the sea water was causing blue light by scattering blue light more than other colors. Raman effect. C.V. Raman and K.S. Krishnan started studying scattering of light by molecules of substances in 1919 at Indian Association of Cultivation of Science Center at Calcutta. Krishnan was the one who first gave Raman a demonstration of the experiment of new scattering phenomenon in a number of liquids. On the 9th February 1928 afternoon, Raman was overjoyed when Krishnan gave him a practical demonstration of the modified scattering using sunlight as the source. On February 28, Raman and Krishnan discovered what has now come to be known as the Raman effect. Krishnan was able to photograph the anti-Stokes line in benzene, and Raman was very overwhelmed with the new development. February 28 is celebrated as National Science Day in India. Every year we are celebrating 28th February as a National Science Day. Raman and Krishnan wrote the first of the 4 discovery papers with the title A New Type of Secondary Radiation that received the name Raman effect and sent it to a Nature journal. During the span of 12 months, February 1928 to January 1929, Raman and Krishnan wrote not less than 14 original papers on the Raman effect. His discovery created sensation in the world, and about 70 papers were published in reputed Western journals on Raman effect, Raman lines and Raman spectra within few months. On November 13, 1930, the Associated Press published news that C.V. Raman and H. Fisher are declared Nobel Prize winners in physics and chemistry respectively. In 1930, Raman got the Nobel Prize. This is the 93rd year of discovery of Raman effect. So this shows the first paper, Nature paper, just shown the paper which I have shown on the screen, so which paper published in the Nature journal. Now what is Raman effect? When an electromagnetic radiation or monochromate light incident on the sample, the scattered radiation contains, in addition to the incident light, the frequencies lower and higher. The frequency which is same as the incident line is called the Rayleigh line. The frequency which is lower than the incident frequency, which is called Stokes line. The frequency which is higher than the incident frequency, which is called anti-Stokes line. When photons strike a solid or collection of molecules, most of them are scattered elastically, so that scattering is called Rayleigh scattering. But a few, 1 in 10 to the power 6, undergo inelastic scattering. These inelastic scattering photons have frequencies lower, that is called Stokes line, and higher, it is called anti-Stokes line, than the incident frequency. Stokes and anti-Stokes line are found to be symmetrical with respect to Rayleigh line. The frequency difference of each Raman line from Rayleigh line is called Raman frequency. Just see the frequency, center line is a Rayleigh line, that intensity is much high. Right side the frequency is higher than the incident frequency, that lines are anti-Stokes line. The same line shift is same in the left side, that is a frequency lower than the incident frequency, that is a Stokes line. But the shift from this Rayleigh line, both are same, but the intensities are different. The reason is, when in the case of Stokes line, the lines originated at the ground vibration level. After absorption of photons or energy, it goes to the virtual level and comes back to the first excited level. Whereas in the anti-Stokes line, when the photon incident on the molecule, the first excited vibration level and goes to the virtual level and comes back to the anti-Stokes ground vibration level. So that line is called anti-Stokes line. So since the population of the ground level is more than the first excited level, so the intensity of the Stokes line is more than the intensity of the anti-Stokes line. So, see, if you record the Raman spectra of diamond, you can see only one band. So, this is the only one method to find out to detect the purity of diamond. So, if there are any additional band, that shows that there are some impurities. If you just record the Raman spectra of diamond, if you get only one band, that shows that the diamond is pure. Similarly, if you just record the Raman spectra of silicon, if you get only one band at 520 nanometer, 520 centimeter minus 1, that shows the silica is pure silicon. Similarly, germanium, the purity you can check using the Raman spectra if you get only one band. If you get more bands, that shows there are some impurities. Similarly, you can be able to find out the purity of pearl, whether it is phosphide or pure pearl or calcium carbonate. From the spectra, you can be able to find out which one is a pure pearl. Then ivory or plastic. So there are in the world there are you can able to distinguish. If you just regard the Raman spectra, you can clearly identify which one is, whether it is plastic or ivory. So that is the only one method to detect the purity of these materials. Then Raman effect first. Raman spectroscopy, which started with sunlight as a source, as a new discovery with the advance of mercury arc lamps and a Toronto source, become an advanced research tool by the 1960s. When we source the sunlight at the source, we need a large quantity of sample and large exposed time is required to get the Raman signal, since the Raman signals are weak, because the brightness available per unit area is very small. So we need a large quantity of sample to record the Raman spectra. So that's the reason only a very minimum papers have been turned up in those days. So after the advance of mercury arc lamps, and also filter is required using a monochromatic light. So that also the intensity is very small. We need a large quantity of sample and large exposed time is required. A quantum leap happened in Raman spectroscopy with the discovery of lasers, and it became a more common spectroscopy tool when efficient photon counting system also become available. At this stage, in the evolution of Raman spectroscopy, investigations on molecular motion, phase transitions, crystal structure and even drug interactions were already started by several groups. With the advent of multi-channel detectors like the CCDs, that is charge coupled devices, Raman spectroscopy came to be used for a multitude of research and routine applications in all areas of science and technology. Raman effect present. Development of miniature laser sources, compact Raman spectrometers and advances in data analysis and data processing is leading Raman spectroscopy to another quantum leap. Multitudes of Raman spectroscopy, surface enhanced Raman scattering, normally called SERS. The sample is placed in a proximity of plasmonic nanoparticles which concentrate and localize the radiation field interacting with the sample, providing intensity enhancement up to even 10 to the power 14 times compared to conventional Raman. This has led to Raman spectral studies down to single molecule levels. Tip enhanced Raman scattering, normally we call TERS, an optical nano imaging technique which overcomes this deficiency by combining Raman enhancement of SERS with scanning near field optical microscopy using plasmon active nano tip. Laser teaser Raman spectroscopy LTRS used extensively at present to study intrinsic properties of viruses cells, aerosol droplets, etc. in various conditions. Nowadays, this technique used for Raman imaging, laser tracer Raman spectroscopy is used for Raman imaging to detect the early cancer. Then spatially offset Raman scattering SORS and transmission Raman scattering TRS used for characterization of molecular species deep inside opaque substances like tissues, commercial packages, etc. Then coherence anti-Stokes Raman scattering. Normally Stokes line is more intense than the anti-Stokes lines, but this technique will give coherent anti-Stokes lines also intense line you get. This is the non-linear Raman technique. Coherent anti-Stokes Raman scattering and stimulated Raman scattering techniques are non-linear Raman techniques which can provide much stronger Raman signals compared to spontaneous Raman. Both techniques can provide chemical specificity and are useful for time-resolved studies. Then resonance Raman studies. Raman scattering cross-section can be increased by a few orders of magnitude by choosing the excitation wavelength to match an electronic absorption band of the molecular species of interest. So if the interaction radiation or the excited radiation is matched with the excited electronic level, then you will get resonance Raman scattering. Normal Raman scattering, the excited radiation energy level just below the excited Raman level, excited vibration level, excited electronic level. If it matches with the crosses with the electronic level, then it is called resonance Raman scattering. Photothermal, photoacoustic Raman, hyperspectral imaging, Raman spectroscopy, hyper Raman, unfocal Raman and terahertz Raman, etc. Combinatory Raman, lip photoacoustic spectroscopy, etc. Then biomedical Raman spectroscopy. Raman spectroscopy with the multitude of non-contact, non-invasive, non-destructive, label-free techniques and with both point of care and remote capabilities started to play a major role in biomedical applications. Abnormal conditions other than malignancy can be discriminated from malignancy by spectral differences in the spectra 1200 to 1300 wave number region. Highly objective classification free from any personal bias of visual observation can be done by multivariate analysis of the spectra. Cell sorting and classification, bacterial identification, diagnosis of various cancers, surgical boundary, demarcation, digital pathology and hyperspectral imaging of biopsy samples, drug resistance studies, etc. Raman effect future. With recent advances in miniaturization of instrumentation and compact multi-wavelength excitation sources combined with advances in data processing and machine learning, Raman spectroscopy is now poised for another quantum jump which will enable its use in the near future in everything from wearables and personal diagnosis to advanced scientific research in a variety of fields. Many groups are working now on spectroscopic systems, data from which can be recorded and processed by mobile apps or transmitted to a central lab where artificial intelligence based data processing can give answers to the problems under investigation. Systems like pocket colposcopes and combination catheters are already being tested and will soon be available for multi-modal spectroscopy in endoscopically accessible organs for screening and early detection of diseases like cancers during surgical biopsy or surgery, etc. Professor Wolfgang Kiefer, eminent Raman spectroscopist, shared his recent opinion about the future of Raman spectroscopy. Yes, a single virus or bacterium can be trapped in a focused laser beam and can be studied for its characteristics and also the changes when antibiotics are used on them to develop effective medicines or treatments. The effect of SARS virus COVID-2 can be studied in great details using Raman spectroscope in a medical environment, and ways of eradicating or treating this virus can be understood in future researchers using this technique. Thank you very much.